Are we all good? So we in the, you guys are probably over the first round of midterms, right? For most classes, right? Okay. Wow, it's does anybody know what that big long line is right next to the Tim Hortons? Everybody's lining up for something.
Oh, they're selling spring rolls.
But the line is as if they were giving like $100 bills, like
They're really good spring rolls.
really, really, really good. Okay. So, well, I hope you got your spring rolls already, but you're gonna get something so much better than that. So, temperature in welding. This is I'm going to talk just part of today's lecture on temperature in welding, but this is something which we have been working since forever, and we have made like really important contributions that are going to come in so handy for you that in the design class. Carlin, and who else is in your group? Right. Okay. That you were like asking me questions about preheat and all those things. I have a straight answer for those, and it's in here, right? So if you already looked at those things, you can ask me questions, and you're gonna see that every final exam in the last many years has questions that relate to this. So temperatures in welding, right? It's one of the most fundamental things, because the whole point of welding is this non-equilibrium that I mentioned in the first class. If you melt everything, that's casting, and that exists. If you melt nothing, would be forging or bolting. That already exists. But the whole point of welding is something is hot and something isn't. So if something is hot and something isn't, you have gradients, you have heat conduction, and then you get into a much more complex problem than the problems people typically use. Now, although it's a very complex problem, we understand it, and by the end of today, you should have a pretty good grasp on that. So this is not something I'm going to quiz you on, but so you have an idea how we are going to address this. What happens in welding is a transient problem, right? Like the steel is cold, the torch passes over it, so it's hot. Then after the torch passed, it got cold again. Right? That's a transient system. So you can idealize these transients, right? And you can idealize it as, you can say, the source is as small as a point, right? And you can say the point is hot and liberates an amount of energy and can be on 3D, 2D, or 1D. We will not be dealing with those exact equations directly, but they are embedded in the things we do. And this is a very interesting thing, because these points, for example, correspond to actual problems. Imagine you're repairing a pipeline, and the welder by mistake is like talking with the assistant or something, and touches the pipeline with the electrode, right? If that happens, there will be a big spark, right? That's called what is it? That's called an arc strike, right? Now, would you think that's a big deal? That the welder, blah, 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 oh, do you think it's a big deal? Yes, it's a huge deal, because, why?
Because starting the arc is a huge energy input, right? Huge energy input.
Actually, you're onto something, but the problem is exactly the opposite. It's a little energy input, right? It was, you melted locally. So to some extent, you have a lot of energy locally. Does it cool down fast or slow? If it is little, it cools down very fast. What do you think you're going to have? You're going to have a hard spot, and those can be a big problem in things that run on pressure, right? So you have to grind them. It's a big deal. Now, if you want to calculate how bad your arc strike would be, we can. There are formulas for all those, right? So that is like a transient point. You can have something similar in 2D, like if instead of being a point that this diffuses heat in 3D to a whole thickness, could be like spot welding in cars, in which the heat diffuses, but in a plane, in 2D. Right? And there are formulas for those, and there are books that deal with those. You can even do it in 1D. Right? For example, at NATE, you were at NATE, right? Did they ever show you this new system for cladding in which they have like a huge flash lamp? It's like a flash from a camera, but multiplied by 10 million, right? And it goes boom, and it melts everything on the surface. Right? If you think a flash is pretty bad on your eyes, well, that thing melts the steel, right? That's a 1D problem, right? And then we could address it with this. Now, imagine that the point, instead of being instant, it moves, right? And that represents welding. Funny enough, and I'm not going to get into the details, if you weld very slow or very fast, actually is the equivalent to these other cases I discussed, right? When you're moving your point, you can move it and have two extreme solutions. That could be what people call the thick plate solution, right? Imagine you're in a thick plate and the heat goes to the sides and to the bottom, right? I prefer to call it a 3D solution. And then there is what people call the thin plate solution that is better called 2D solution. For example, if you're welding on a sheet, right, the heat goes only to the sides, cannot go up and down because the sheet is very thin, right? However, if you're doing, say, electron beam on something thick, that's not thin at all. But if you have a keyhole that goes all through it, then it's a 2D problem again, right? If you're welding a plate and you're doing full penetration, single pass, that's a 2D problem because the heat moves to a side, doesn't move much top and bottom. So we have a 3D solution, 2D solution. Funny enough, there is even a 1D solution that would apply to the melting of an electrode. We're not going to worry about those. So all I want to talk about today is about these two types of heat sources, in which we're assuming is a point moving in a straight line at constant velocity. But the reality is more complex than that, right? Like you can have a distributed heat source. In reality, your weld is not a point. Actually, more resembles a Gaussian. People have measured this. It resembles like a Gaussian distribution. And arc welding, laser welding could be what people call a top hat. Do you know what, when people say a top hat, what they mean? Something that the heat source would be like constant and then goes to zero. Right, like a top hat, right? Constant. So instead of varying like gradually, and that's used for laser treating. And also you can have volumetric heat sources. Instead of being the heat applied on the surface, can be the heat applied in the volume. For example, if you're doing electron beam welding at the micron scale, the penetration of the electrons under the surface is more or less the same penetration of the weld. So that's a volumetric heat source, and there are other things for modeling them. About these, I included some formulas in your set of slides. The things I'm going to share with you are things that we published this year or that we aim to publish next year. Super advanced. Nobody has this. So here we have the 3D I was talking about, is distributing heat to the sides and to the bottom. And it's called 3D because also there is front and back, right? And in 2D goes only to the sides. This is a case of a thin plate, but the plate can be thick. But if you have a keyhole, it goes to the sides. Of course, let me tell you, reality almost always falls in the intermediate thickness. And I don't have formulas for those for you, except that you're not far at intermediate thickness. You're not far from the thin or the thick. So when you use either thin or thick, it's not all that far. So questions, why does temperature matter? So these are questions that people ask in real life. Okay, remember these formulas I gave you for calculating hardness? Those formulas are amazing, by the way. You use one of those in the exam, and I don't know if you compare it. It gives you within 10% what the CCT says. So the people in East Germany measure that, and then in the exam you just calculated it. And all the work that the slaves in East Germany did for weeks, you could do it in the 10 minutes of the exam, right? But what you needed for that, you need a cooling rate, right? And so that you did it for pure martensite, but if you want to see what is when a mixture of in the bainitic region, you need a cooling rate. These formulas will give you that cooling rate, super important. What is the width of a weld? very difficult. If you ask pretty much anybody today, outside our group, they will give you one of two answers. I'll weld and tell you, or I'll go to my computer and simulate it and tell you. But the weld cannot be that difficult to predict. So you will be able to say, the width of my weld is this. And you will be able to say, okay, the thickness of my heat affected zone is this, and this is the way preheat affects it. So I think I showed you these slides before. So this is a cross-section of a weld, and here is the plate. Here you have a kind of a top hat, right? These are the temperature distributions. This essentially says, is the temperature distribution in the melt, and this would be above the melting temperature. I'm going to show you that it doesn't look flat like this. And then after the torch passed, the heat starts to distribute. And all these are kind of Gaussian shapes. The heat starts to go to a side, and here goes to this side. And as the heat goes to a side, of course, by conservation of energy, whatever you lose to the sides, you lose from the top, right? The integral of this curve is more or less constant. So what happens here is very interesting. For example, you get to see that some points get very hot and then they get cold. And some other points, for example, start getting hot and then they start to get cold later. They have different peak temperatures. So this is a cross-section, a cross-section of temperature profiles. Here would be a side view, right? And the side view, if the weld is moving at a constant speed, you can think, well, this is the temperature profile, and my weld, in this case, the torch is moving to the left, right? In this case, the torch is moving to the left, and these are temperature profiles. Or if you put a thermocouple, this would be, the horizontal axis would be like time. Would you agree with me that time and space are essentially the same axis now? It's not relativity, but if the torch moves at constant velocity, time and distance are related by this constant velocity. So it's like relativity, isn't it? Okay, so here we have 1, 2, 3, 4, 5, right? Here we have 1, 2, 3, 4, they missed the 5, but it's as if they had put a thermocouple in each of these points, 3, 4, right? So if you put a thermocouple at point 1, you get to melting temperature and then cools down. If you put a thermocouple at point 2, it gets hot and cools down, but doesn't melt. So the peak temperature now is changing. This matters a lot, because as you guys know, if I don't reach austenization, I'm not going to have all these hard faces, right? I might have temperate zone, right? This peak temperature is what gives me the important features of the heat affected zone. And as I move farther and farther, the heat gets high and then cools down, right? So the maximum temperature decreases with distance. The maximum temperature in 1 is higher than in 2, higher than in 3, and it keeps decreasing. Now, an interesting thing that is very important, the cooling rate for typical cases of welding, the cooling rate all within the heat affected zone that is like a band around this weld, the cooling rate is more or less the same. So this is a very important thing. And if you read previous exams, you would see I have asked that. Why do we see these very different features in the heat affected zone? Some people might be tempted to say, well, different cooling rates. Completely wrong answer. What gives you the different microstructures in the heat affected zone is the peak temperature. The cooling rate is more or less the same. Not exactly, but you know what? Let's not worry about that. The peak is by sure the dominant. All right. So this is an image we took in our lab with a thermal camera. Right? This is welding of a pipeline. And this is what I'm trying to show you here. In what direction do you think we're welding? Top to bottom or bottom to top? Hmm? You say from bottom to top? I think it's top to bottom, right? This looks hotter than that. Right? It's a wider, like.
It's narrower.
Here? Yeah, it's narrower at the top. right? Because here is the heat is here, and the heat is kind of slowly going away there. But what is interesting here is this was a real guy doing stick welding. This is nothing so advanced. In what direction do you think the heat transfer is? The heat transfer, the conduction heat transfer. It's pretty much to the sides, right? You see the gradients. These are like parallel bands. Not exactly here. You can see that, but these are more or less parallel bands. I'm going to come back to this, right? But essentially, the weld is moving so fast that the weld left the amount of heat and keeps moving, and the heat barely is moving out, right? The relationship between the travel velocity of your torch and the velocity at which the heat goes out is the torch moves much faster than the heat moves out. Right? I want to plant this intuitive concept in your mind because it matters to discuss later. Now, if this weld was done in aluminum, do you think this would be the same? The relationship between the torch speed and the velocity of heat transfer? What do you think? If the weld was in aluminum?
It wouldn't be the same.
No, it wouldn't, right? Because aluminum is a fast conductor. So here's an important thing. This I would call a fast weld, all right? Because I moved fast, but the heat moved out slow. Now, if I do the same weld, but in aluminum, it might not be a fast weld. And people would argue, hey, but I'm moving at the same speed. What do you mean? Well, yeah, but fast or slow depends on the relationship between your torch motion and the heat transfer. If you change the heat transfer, now the concept of fast or slow, which is relative, changes. All right, this you know by heart. So, oh, by the way, I think very select few of you didn't know the iron-carbon phase diagram. You have to know it if you're in MADI, right? The iron-carbon phase diagram. All right, so how do we go about the answer? Well, I mentioned to you, you can do a trial and error that for questions you might have from hardness to size of the weld. You can go to your computer. What I want to teach you, to share with you, is work we have been doing over years in trying to generate formulas for this. But these formulas we didn't invent. I'll tell you more about this. Well, we made the formulas, but the root of these formulas we didn't invent, and it's a formula that looks like this. They are called Rosenthal solutions. So no, we'll not be playing with numerical simulations, although if you wish, we have all kind of software to do it. So if any of you is interested in numerical simulations of this, come to the lab. We have anything anybody can ever want. And if you want to try by hand, we are ready to, right? But I think this is where the real value is, having a simple formula that gives you an answer. Look, to put this in context, this is Professor Goldak, who also has an appointment with our lab. Professor Goldak is the guy who almost, you could say, invented the computer simulation of welding. Extremely famous person. He's in his mid-80s or past the mid-80s. He goes to work every day. He still runs a research group. He's a guy I want to be. He's happy. He's amazing. He used to go running until a couple of years ago. So he developed a model for welding, a computer model. And to do this model, it cost him about $20 million. 11 from government money and 9 in a company he started. $20 million, right? And about 50 years of work. Now, my question to you, in this graph I put, okay, the cost of making a simulation, it gets bigger and bigger with complexity. Now, you can have a prototype, right? It's very cheap to make a weld. The prototype of a weld is cheap. But if you wanted to make an airplane, it's very expensive, right? So you tend to simulate airplanes with computers, right? It costs billions of dollars to make a prototype of a plane. You save money by doing a simulation. But in welding, you come and you say, hey, I can predict your weld with $20 million and 50 years. And then I'm going to say, hey, don't worry. Hey, Joe, go and weld it. And then you know. So one problem we have in welding is that we either weld it, and we are not engineers, we are just like a trial and error, or we go with these simulations that are kind of completely out of the ballpark for welding. They're good for jet planes, right? So what I'm trying to bring up to you is, if we have these type of formulas, now we lower the cost of you making a prediction the way you have done it in the exam. We lower this cost, and now when you have a question about welding, you don't need to go to 50 years and $20 million. But sometimes you can say, no, Joe, stay there. Let me do a couple numbers, and then I'll tell you what to do, right? That's my hope for you, right? Sometimes you just go and try, but not all the time. Maybe you have a pressure vessel that is pretty tricky, and you'll know how to go about it. All right, let me tell you about Rosenthal. The root of these formulas we're going to discuss comes from 1904. There is a guy named Wilson who already worked on this, not for welding, but for moving heat sources. Then independently, this Daniel Rosenthal in the West and Rick Allen in the Soviet Union started to rediscover the formulas I will teach you. The Rosenthal was a super colorful character, was a Jewish guy in Europe at just before World War II, and was not good to be Jewish in Europe at that time, right? So he was in Belgium, I think, and he escaped, right? Escaped the Nazis, went to the US. He landed at MIT, and at MIT he wrote this paper. That is an amazing paper. I have not uploaded to you, not to burden you, but if you ever want to see the paper, I'll send it to you. It's amazing. Where he has a formula. At the same time, the Soviets were doing this in the Soviet Union. The funny thing about about Rosenthal is, after escaping the Jews and being an amazing professor, he ended up in California. He started to grow old, and old, and he would never die. And he was afraid that he would become like a vegetable, in his words, and be good for nothing. So the guy jumped off a building. Crazy story, right? So what did he do? And this is like the foundation of much of the modeling of welding. He went for a completely ideal approach, right? Like a spherical horse of negligible mass, but it's very predictive. So he said, I'm going to model welding as moving in a straight line at constant velocity, which most of the time is true. So he said, we're going to work in a pseudo-steady state, which means once you started welding and things get more or less established, like just they keep going. So you don't worry about the starts, and you don't worry about the end. The guy in the Soviet Union did the derivation slightly different, and he did the starts and the ends. But let's not worry about starts and stops. This is just when you're moving at constant velocity. He said, let's weld something that is super long and super wide. Right? And of course, such a thing doesn't exist, but things close to it do exist. He said, the heat transfer will be either 3D, right, or 2D, not intermediate thickness, although he eventually did it too. Then he said, hey, my weld is going to be super small, right? It's so small that it's a point. He said, okay, specific heat, thermal conductivity, I'm going to call them all constant. And it's kind of true, but kind of not true. For example, how about latent heat? Right? Latent heat gives you a big spike in specific heat. He said, let's go for it. Let's not worry about that. Right? And then he said, if the plate is thick, let's not worry about heat losses on the surface. If the plate is thin, we can deal with it. Right? So he had the formulas I'm about to show you, and somebody following him, Niels Christensen, in somewhere in Scandinavia, right? He made lots of welds, cut them up, measure them, and measure the cross-section of the weld and the with or without the reinforcement. And what you get to see here is these lines are the lines from Rosenthal's formulas. In dimensionless forms, so everything falls on the same line. And the points are the points for very different ways of welding, whether it's stick or sub-arc welding or MIG. What do you get to see here? All I want to draw your attention is Rosenthal had a formula, and the formula is a line. Christensen did 1 million experiments, and the experiments are these scattered around the lines. I would say it's pretty good that we follow the scatter, right? That's pretty good. Now, on the other hand, if you see the scatter, the scatter is like half a grid line up and half a grid line down, and each grid line is an order of magnitude, right? So it's like a factor of 3. You can be off by a factor of 3. I think in our own experience, every time we measure things, we're way better than a factor of 3. But this is good, but it's not perfect, and the imperfection can be significant at times. That said, I'm going to take them as if they were perfect. And if they are not perfect, we'll discuss. But with a simple formula, I'm now better than the guy who knows nothing. Okay, let's talk about the Rosenthal solution for 3D. You do not need to memorize this. You seldom need to use this formula. And here in the formula it says temperature of x, y, and z in these coordinates. X is in the direction in which the torch is moving. Is T naught. T naught is the preheat. So right there, when you were asking me about questions about preheat, here we capture it. Q is the power of the heat source. These are the watts. And these are watts into the plate, right? So this would be the volts times current times efficiency, right? Because this is what goes into the plate. K is thermal conductivity, right? And this is tabulated. This is not a welding property. R is like the radial coordinate in polar is a polar coordinate, right? Is the distance from the center, and the center is where the point heat source would be. And U is the travel velocity, alpha is the thermal diffusivity, and X is this direction here. So with this formula, I can give you the temperature pretty much everywhere on the plate, right? Give or take. So this is the solution for 3D. We seldom, if ever, are going to be using this because people like ERTA Louis and many others in the lab have spent years and ungodly amount of hours processing this to give you something useful. So far, the welding books will give you this formula, but this is seldom useful. I want you to be familiar with it, but it's seldom useful. Now, if you have a 2D solution, which would be a thin plate or keyhole or full penetration, a single pass, it's very similar. Now it's not X, Y, Z because it's 2D, it's X and Y. You have T naught, which is a preheat, Q, that is efficiency times volts times current or whatever amount of heat gets into the plate. K is thermal conductivity. D is the thickness of your plate. Now we have an exponential velocity times coordinate X. Alpha is thermal diffusivity. K, here things get funny. Chances are you haven't used much of Bessel functions so far. You might have seen them in heat transfer, right? When we have the solutions for transient heating in cylinders appeared. Okay, you don't need to worry about it. If you want to use Excel, it's in Excel. But as I mentioned, we shouldn't be using these formulas. This is Bessel function of this argument. And this argument here has the convection coefficient on the surface. To give you an idea, this convection coefficient is typically negligible if you're talking about things at the temperature of like T85. Seldom need to worry about H. You need to worry about H if you're talking about low temperatures. You're going to see then when we talk about residual stresses, the residual stresses form at temperatures like 100 degrees. right? So that's very far from the weld, and that matters. If you're doing underwater welding, you need to worry about this H. And if you're doing in-service welding, in which you weld in a pipe that is carrying a fluid, you need to worry. But for most other things, like welding normal things, you do not need to worry. So now I'm going to say, let's forget about this for now. And if you ever care about this, you talk to me, because we're working on it too. But I don't want to confuse you. Now, here we have, don't worry about these coordinates. Someday we're going to make them better, these kind of indications. But here we have what the isotherms would look like. This would be the x-axis. This is temperature, as I showed you, right? And I showed you the curve before. And these are the isotherms. And as you get to see, the isotherms look like an ellipsis. They're not exactly ellipses, but they look like ellipses. And this is at high temperatures, and these are the ones at lower temperatures. Conversely, you can say the long ones are for high velocities, and the smaller ones are for smaller velocities, right? You would agree with me that if you don't move, by symmetry, everything should be circles, right? By symmetry, if I'm not moving, the heat would go the same in all directions. So this is what happens when you move slowly. When you move fast, you start to leave a trail, right? So whether you say move fast or slow, or I care about high temperatures or low temperatures, the curves are going to look like this. So this fast and slow, combined with the temperature, there is something called the Recalling number, or the Rosenthal number, that I thought I had invented, but I didn't. I invented it, and I said, I'm writing my paper, I'm doing the literature search. Sure enough, one of my good friends, Phil Fiersbach, had figured this out and published it before. And these numbers are something similar to the Reynolds number in fluid mechanics, right? All of you took fluid mechanics. And all of you at least heard about the Reynolds number, right? And you would not do pipes. You would not calculate anything on a pipe without using Reynolds number. You cannot design an airplane without Reynolds number. For welding, we have something similar that is called for the Recalling for the 3D solution, or Rosenthal for the 2D solution. And these numbers have this expression. I'll tell you more in a minute. But I'll tell you what the meaning of these numbers are. Remember when I showed you the photo of the thermal image, and I discussed how the relationship between moving the torch has a velocity, and then the heat expanding is another velocity. These numbers, and you can prove it by working the math, but you don't need to worry. These are the ratio between travel speed and the velocity at which you diffuse heat, right? So if I have a high Recalling or I have a high Rosenthal, here the U doesn't appear, but don't worry about it. In the end, it's because it cancels. That means if this is typically bigger than 1, you're moving fast. Less than 1, you're moving slow. A little bit like Mach number, right? But Mach number is for compressible flow, and this is for something else. And what do you get to see here? Remember, for example, I said faster welds would give you higher Recalling, but I said lower temperatures also would give you this elongated. Here you have temperature in the denominator, right? And how we arrived to this, I'll be super glad to discuss with you, but you don't need to know it for the class. We make a living out of this, so for sure, ask me and I'll be super glad. So this is an indication of fast or slow. Then we have another dimensionless number for thick or thin, right? And we call it D star. The star means dimensionless, and is velocity times the thickness over the thermal diffusivity, 2 times that, right? I don't know if you remember, but this looks very much like a Peclet number. Right? I don't know if you remember, I don't know if you care, but that's what it is. But that doesn't really matter. What matters is this: fast or slow. If you ask me, am I fast or slow? I'll say, no problem. I'll look at the recalling and I'll tell you fast or slow. And then you can ask me, is this thick or thin? And I will not ask you, what is your thickness? I would ask you what the D star is. Based on these two things, I can determine fast or slow, or thick or thin. And we made this map for you. And again, we did this ourselves. We're not the first to say the map. And here you have one that was done by Gronk, that was a student of Christensen. And so in this map, here you have recalling that you calculate with this formula. Here you have this D star, which you calculate with this other formula. And if you say, OK, I calculate recalling, and you know, here you have the power of your heat source, travel speed, thermal conductivity, thermal diffusivity, what temperature you might be caring about. It can be melting temperature, can be something between 800 and 500. Here is preheat. So you can calculate this right there. For this weld, this, and same with the D star. And you see where you fall. If you fall here, you say, oh, I'm fast and thick. If you fall here, you say, OK, I'm fast and thin, slow and thick, slow and thin, right? We will do concrete numerical problems with this. Where is reality? OK, let me show you. This was the final project of guys many, many years ago, when we were first starting to learn all these things. So they went to the Lincoln Procedure Handbook, which you have, and they transcribed the parameters for submerged, for stick, for MIG, for flux core, for TIG, for submerged welding. And we got additional data for laser cladding, friction stir welding. We got lots and lots of data. And this is what we got. Processes like submerged welding, right? Those are fast. Those move fast. They put this huge amount of heat that takes long to dissipate. In submerged welding, you tend to see very elongated weld pools. Conversely, in friction stir welding of aluminum, you move very, very, very slow. If you do TIG welding of aluminum, sorry, here it says MIG, but we have TIG welding of aluminum somewhere. OK, we used to have it separate, the TIG welding of aluminum. But if you weld aluminum, you tend to be on the slow side. Big welds in steel tend to be on the fast side. But most life works within this circle, and this circle is neither intermediate thickness, intermediate speed. And yeah. There is another thing here. If I were to have a weld that is a single pass in full penetration, right? Single pass, full penetration. Do I need to use this graph to know if it is 2D solution or 3D solution? No. We know single pass, full penetration, that is 2D, right? Even if the plate is like this, right? Well, if it is like this, you better have a good electron beam, right? Like this, right? 10 centimeters is about the limit, not this. OK, so my whole point so far was this. Welding, it can be fast or can be slow, depending on a combination of travel speed and materials properties, and can be thick or thin, depending also on a combination of parameters. And if it is single pass full penetration, it's 2D. Now, I put here for your reference something that is going to be in your formula sheet too, and it is some parameters. For aluminum, carbon steel, efficiencies. Remember, we discussed a lot about efficiencies, how to do it right. But here you have some ballpark values from literature. If you ever wanted to care about convection, we put it here. But here is the real cool thing of the class. See this? Those of you who took heat transfer with me and remember in Cropera book, the textbook we use, and the convection unit that said for this pipe you use this formula and you check the Reynolds. This is the same. But the cool thing here is we did it. right? These are things we did. So these amazing students that we have in the lab have grabbed the equation of Rosenthal and did all the math to calculate the maximum width or the cooling rate or those things. So you should never use Rosenthal, because they already spend like years of their life doing math that is very difficult to give you these formulas here. And I uploaded the paper so you know how to use this correction factor. But if you don't use the correction factor, I'm fine for now, right? Unless I tell you to use it. But I don't think it's also important right now. Here we have this. Okay. I changed the slide today and I forgot to add something. But please add in your notes, this regime 1 means thick and fast. Regime 1 means thick and fast. Or 3D fast. And regime 2 means 3D slow. Ymax is a formula to calculate the width. You can calculate the width of your weld with this now. This is the half width. Let's see. Here. Y is this axis, so Y maximum would be from here to here. It's a half width. So the total width of the weld is 2 times this, right? So you can calculate the width. You can calculate where it becomes where you reach this maximum width. It's not so useful. This is XB is the length of the weld pool. This point here, XB, the length of the weld pool, the length of your tail. Later, this is so wonderful. For example, remember when we discussed in submerged arc welding, we use fluxes, right? What prevents us from using gas for submerged arc welding? How about if I were to shield it with gas? What would be the problem? I mentioned this briefly. I don't know if you might remember.
You're blowing away the fluxes.
Well, let's forget about the fluxes. Let's do a super big MIG at 1,000 amps. So what would happen is you have a very long tail that you can calculate. This XB, you can calculate it using this formula. And if the tail is very long, it's outside your shielding, right? And you get all kind of porosity. Now you can calculate all these things. This is quite amazing. This is the cooling rate at the back. So this is how many degrees per second you're cooling. This is the position at the front of the weld in here. This is the heating rate. Remember when we discussed about heating, how the A1 and A3 during heating, they move up? Okay, so that's quite sophisticated. But if you want to say, I know my material well enough that I can tell you A1 and A3 from if you give me the heating rate. Well, sure, I'll give you the heating rate. And you can calculate the maximum temperature for a given width. This is the peak temperature, right? At a given width, what is your peak temperature? All right, here you can calculate for a given width your peak temperature based on all these things you know. E is the Euler's number, pi you know, and all the rest you know. Plug and chug. 3D, here more 3D characteristic values. T85, we have talked about T85 a lot here. Remember when we talked about melting efficiency, right? Melting efficiency, you can calculate melting efficiency here. And here you come to a conclusion, if you move very fast, melting efficiency goes to 1/E, and I forgot what that number would be. Would be like 0.4, something like that. And if you move very slow, the melting efficiency starts to go down and down and down. just for the sake of exercising a bit, I'm showing you a million formulas. But if I'm moving slowly, my melting efficiency is low. Why? Other than the formulas. What's the physical reason melting efficiency is slow?
I'm melting my plate instead of my electrode.
Say it again, you're melting?
The plate more than the electrode.
Well, in the melting efficiency, actually, it's the relationship between how much heat you use to melt versus how much heat you put in total, right? So it would be if you're melting less plate than the electrode, right? And it's true, that would be true. Okay, so melting efficiency was, for having a given weld bead, what is the minimum heat I need, right? And you say, okay, enthalpy of liquidus times the cross section. That's a minimum heat I need. Am I giving it the minimum heat? No, you always give it more. Why do you give it more? Well, you give it more because some of the heat escapes on the sides. And the heat that escapes on the sides is heat you put in, but it's not used for melting. It just went away. If I move slow, welding is like putting water in a leaky bucket. You put the water and the water is falling out. Now, if I pour water in my leaky bucket very quickly, right, and then I fill it up quickly, even if it has a leak. But if I have a leaky bucket and I put water very slowly, I put the water and leaks out, put the water and leaks out, right? It's going to take long to fill up. And actually, if I put too little heat, it's never going to fill up, right? So this relationship between the heat we put and the heat we leak to the sides is captured here in this melting efficiency. All right, thickness of the heat affected zone. Right, we have two ways of calculating it. This is actually, this is exact if we use this intermediate temperature. So what is the heat of my heat affected zone? All right, melting temperature, this would be temperature of the heat affected zone. Let's call it A1. If we were to say the edge of a heat affected zone is when we first start austenitizing. Ti would be an intermediate temperature between melting at a heat affected zone. You can do many things, but if you use this one, you get an exact answer, right? And this is the preheat. So if you ask me, if I were to increase my preheat, all things being the same, if I do this exact same weld and I increase my preheat, what happens with my heat affected zone? Is thicker or thinner? Thicker, right? If I increase my preheat, this increases, this gets smaller, therefore the heat affected zone gets thicker. So with these things here, you can already say things that are not intuitive, are very, very difficult to address. But now you can. Now you can say and you can act on it. All right. There's an interesting thing that Mitch will discuss with you in the seminar about the effect of bevel, the effect of joint preparation. And it's a super cool thing because when we talk about welding, we're assuming it's a thick plate, right? But if instead of being a thick plate, it's a bevel preparation, if the plate is thick enough, right? This happens when the plate is thick, but you do the bevel. I'm going to ask a question to you. What do you think has higher cooling rate? If I weld just on top of the thick plate, let's say that this is a thing that is, I don't know, 4 inches thick, right? If I weld it right here 10 centimeters, if I weld here on top, I would have a cooling rate. And I do the exact same weld here at the root pass. Would it have, the root pass would be faster cooling, slower cooling, or same cooling? What do you think?
Cooling is the same.
Okay, I heard all three now. So you say cooling would be the same. Why?
I'm just thinking from the schematic of the heat affected zones.
Mm-hmm.
There more or less the cooling rate doesn't change, the peak temperature would change.
Okay, okay, so maybe let's put an asterisk to that. Who said faster? Anyway, okay, why would you say that?
Because that area has less molten metal.
Less molten metal, right? Let me think. If the weld has the same power, you're melting more or less the same, right? I'm saying the same parameters. The same parameters I use here in the. Actually, by the way, you don't do that because in a root pass, if you use like the same power as the top, you destroy your root, right? It's too powerful. Somebody said slower. Why?
Because there is less area for the thing to escape.
Exactly. So if you do the mathematics, you realize that if I were to weld right here, I would have all this area to escape for the heat to escape. But if I weld right here, I have only this sector to escape, right? And so what is incredible is all these formulas I showed you here, all these crazy ants on the board, but you can predict what would happen if you do a root pass in a thick plate. You can predict it by assuming that you just put more heat. It's like instead of using Q, you would use an effective Q. And it's 180 degrees divided, phi in this case, divided the amount of heat you're putting. Here, half the Q goes here, the other half go this way, right? So what the plate thinks is that you're putting more heat than you're putting in reality, right? And that's when you said you would melt less metal, is maybe because you know enough as to know you should lower the heat, right? But I was saying, just for the sake of the example, let's not lower the heat. And the equivalent result is it went up, right? So now you can calculate what's going to happen in a root pass. Super powerful with all the math we already did. We can make predictions if you have an asymmetric groove, for example, a single bevel. I can tell you right now that you should put more heat on this side than on this side. And the welders already know this, right? They would spend more time dwelling on this side of the plate than on this other one. And the reason is this is sucking up heat over 90 degrees, and this is sucking heat over 60 degrees. So this cools faster than this. All this is you can do with the same analysis we did, and in these cases, we can understand intuitively. Mitch will have an example of this using actual pipeline procedures. Wow, how about this? So again, let's not worry about, these are correction factors. I want you to have them, and if you ever care, we can discuss, because they are useful for many things. Here, if you can put in your notes, regime 3 means 2D fast. And regime 4, of course, is 2D slow. And here you have what formula to use. If you calculate that the solution is 2D, then it's 2D for sure. Sometimes you calculate that it's not 2D, but you know it's full penetration single pass. Then you can use the 2D OK. And this is, to some extent, this might look intimidating. I would agree when you look at this and you see so many formulas. You don't need to remember any of these. And all the formulas use the same thing. Power input, watts, velocity, thermal conductivity, thermal diffusivity, thickness. You have this thing, gamma, that I don't know if we put, OK. I'll update this and tell you gamma is a constant. Gamma is a numerical constant like pi. But it's not pi, it's something else that I'll give to you, so it will be in your formula sheet. But this is not a material parameter. This is a constant like pi. You just plug and you get a number. This is so amazing, and you can answer so many questions. Heating rate, cooling rate, width, maximum temperature, thickness of heat-affected zone, T85, right? Melting efficiency, and I didn't, okay. It's not in here, but in the previous one, you could even calculate, this is a cool thing. This one, TSL, is solidification time. Remember when the president of AWS came here on the first week of class, and then he gave a lecture that we, at the time of our seminar, right? And he was talking how for additive manufacturing, he was cooling down this P91 material very fast, and he was getting a weird microstructure. And he calculated the cooling rate using dendrite spacing, right? And he calculated 10 to the 5 degrees per second. That's a crazy number. You never get that, but he was getting that. And we used this same exact formula you have here. The same exact formula you have here, and Louis put in the parameters for this P91. And guess what we got? 10 to the 5. Dead on. This formula is so important. It's extremely powerful, what you guys have here. So you have all these things, and here you have thickness of the heat-affected zone for thin plates, T85 for thin plates. And this one, you know what? I wanted to include it, but I think it's a little bit too much to discuss. But what this aims to is, remember when I told you if you put too little heat, you're not going to fill the bucket. If you put too little water, you don't fill the bucket. If you put too little heat, you don't melt. These are the formulas that tell you if you would melt or not. But I think I showed you so many formulas already that I don't want to overwhelm you. These formulas are gold. They're real gold. Anyway, I'll show you. I'll just point at things in this example. Mitch will go step by step over this with this. And this is an example from the final last year. How do you use these formulas? All right, here we have an example. Say for MIG, estimate the thickness of the heat-affected zone. Assume this travel speed, assume this voltage, assume carbon steel. 718, it would be the A1 temperature, right? So in this case, I was giving it, but I might ask you for what should be the edge of the heat-affected zone, right? Give me a number. If you have a CCT or if you have a phase diagram, you should be able to give a number. All right. So they, okay, so let's assume a flat plate. All right, how do we go about this problem? First thing we have to do is to see where we land on the map, right? So to know where we land on the map, we need to know the D star, and we need to know our recalling. This map will be in your formula sheet. So you calculate D star, that is velocity times thickness over 2 alpha. Velocity, I gave it to you. Thickness, well, that was when it says the case of question 3, but the thickness was given was 1 inch thick. Alpha, this is the thermal diffusivity that comes from the tabulated values that are in your previous slides and in your formula sheet. Right there, you calculate D star, 8.5, let's call it, 8.5. 8.5, the D star, 8.5 would fall here. This is log scale, right? This is 8.5, this height. Now we have to calculate recalling. All right, Q. Q was efficiency, thermal efficiency times voltage times current. You do this calculation, you get 6.6 kilowatts, fine. U, that's the travel speed, same as we had it here. 4 pi k. K, that comes from these tabulated properties. Alpha, tabulated properties, the same one we have here. And then now we have this intermediate temperature for calculating the heat affected zone, right? So the heat affected zone goes between A1 and melting. Okay, so let's put something in between. I suggest that you use 1045 degrees C, but you would have known. You get A1 that is 718, melting that is 1400, something like that. You do the average, you get a number. In this case, I gave it. In this case, okay, somebody tell me, am I using preheat, yes or no, and if yes, how much? 20 degrees. So let's call it no preheat, unless we're welding in Fort Mac in the winter, and 20 degrees would be preheat, right? So 20 degrees, no preheat. These formulas, they look simple, but they speak. You know no preheat. You know the economics of no preheat. And if you ask me for preheat, you would know, okay, what happens. In this case, we calculate recalling. 8.5, let's call it, right? Same as before. It's 8.5, go here. So you see here, in the old diagram, I had 1 and 3. So this blue dot, this lands in the fast and thick, right? Your formula sheet is going to be labeled 1, 2, 3, 4. Fast and thick. Now you know what formulas to use. So in your formula sheet, you would go to fast and thick or fast and 3D. Let's use proper terms, right? Would be 3D regime 1, whatever question they are asking us. In this case was thickness of heat affected zone. Okay, this is what I would use. Regime 1, right? 3D fast, I have a formula. And this is what we did. Oh, here, look at that. Formula sheet, here it says thickness of the heat affected zone. And you just plug and chug. You don't need to know how to derive this, but you must know what Q is, what alpha is, K, U. You put it, and you just calculate. You're going to do this with Mitch step by step. But what does it say? That the heat affected zone, in this case, is short of 3 millimeters. And this is more or less right. These formulas are incredible, because something you can do in an exam is giving you values that would take you lots of time and money to obtain experimentally. So if in reality it's going to be exactly 2.9, I'm betting money that it's not. But it's not going to be 29, and it's not going to be 0.29, right? And you can start troubleshooting your procedures. You can start saying if things would be good or bad or what to expect. And by the way, we never got numbers that are too different than the prediction the few times we measured it. Heat affected zone were especially good. All right, so this is, there are some other examples that in the set of slides, and there I uploaded all previous exams. When you go through previous exams, you're going to see how the class was evolving. This thing I'm teaching you now is so much better than what we taught 2 years ago and 3 years ago. So as you go over all the exams, you're going to see that the way we structure the answer key is not as elegant as what I'm suggesting now. What I hope you'll do in the exam is this, right? What stands as valid is what we teach here in class, right? So if you do problems from previous years, in preparation for the exam, follow these steps. Calculate D star, calculate recalling, see where you fall. And then you use the formula. Imagine you don't know. I'm asking you things like calculate travel speed or calculate power. Well, if I ask you that, you cannot calculate recalling or D star. So in that case, you assume. You say, I'm going to assume I'm fast and 3D. You assume that, you do your thing, and then after you got the answer, then you come back and say, okay, was I fast and 3D? Maybe you were wrong, right? in reality, then you do everything again. For us in class, as long as you are systematic, right, and you say, I'm assuming this, therefore I got this, and I'm going to check now, okay, that's okay. If you say, well, I assumed something wrong, it's not your fault. You had to assume something in ignorance. All right. Any questions about this use of temperatures? These calculations? Please look at all the exams. The core of every exam we have had in previous years goes through an example like this. This is from last year's final. This is gold. These formulas, combined with the formulas for hardness I gave you, you can make a model of weld today. That is big money. It's big money. Very few people are able to predict, to speculate about what hardness you would get in a weld. Very few people. And nobody can tell you what your heat affected zone would be, and many other things. So, or what the size of the weld would be. This is cool. All right. So, in this time we have about 15 minutes. I want to. My suggestion is, if you're going to spend some amount of time in preparing for the exam, just go over all the exams and start trying your hand. And if you start early and you have some questions we can discuss. In my mind, it's self-explanatory, but professors always think it's self-explanatory and easy, right? But you have the worked out examples from previous years. That should help you quite a bit. So I want to talk briefly about the Weld Pool. And the weld pool is the part that is molten as you weld. Of course, there's no weld pool after you finish the weld because everything was solid. But as you're welding, you have all this molten metal right there. The weld pool is extremely complex. Except electrostatic forces has pretty much everything you want. You want electromagnetic, capillary, heat transfer, fluid flow, phase transformations, everything. So quite complex. Funny enough, all these formulas I showed you assume there's no liquid, that things behave as if the weld pool was just part of the solid. Now, after doing all those formulas that are so useful and so practical, now I want to tell you, no, some of the things that Rosenthal said are of course are not true. He said them for convenience, but let's see what the implications are. So, first of all, I want to discuss what is the maximum size of the weld pool. Why do all welds look the same? Just think of this. You're welding a car. You're welding a motor. You're welding a bicycle. You have a weld bead. Now you're welding an aircraft carrier, and your bead is more or less the same. Isn't that crazy? If the thing is 1,000 times bigger, shouldn't we have 1,000 times bigger bead? Have you ever thought of that? It makes no sense. If you're machining, big things have big cutting tools. But in welding, it's not like that. The reason for that is that in welding, you have gravity, at least here on Earth, and then you have surface tension. What keeps your weld together is this combination of surface tension acting against gravity. So if you were to have something that is too big, the weight of gravity would win and would scatter. So you're familiar with this because if you have a droplet on the fall, it's a droplet, right? If I put a little bit of water here, it's going to stay in the form of a droplet. But if I come with a bucket and I dump the bucket, it's not going to be like a big droplet, right? It's going to flow all over. That's what happens in welding. There is a dimensionless group called the bond number that relates these two things. That it relates the effect of gravity on top, and the effect of surface tension in the bottom, right? And this is a very rough thing. So if bond is big, that means you have a bucket that is splashing all over. If bond number is small, you have a tight droplet, right? I hope none of you played with mercury, but I did. Any of you would know what I'm talking about? Have you ever tried to pinch a ball of mercury? Well, there you have the effect of surface tension versus gravity, right? I hope you didn't have as bad consequences as I did, huh? So that's the effect. So let's say, for the sake of the exercise, let's call bond equals 1 as the limit. It's not exactly 1, but since I don't know what the number would be like 2 or 0.5 or something like that, I'm going to call it 1. And I say, if it is more than 1, splatters. If it is 1, it's a ball. All right, so I solve bond equal to 1, and I get this formula. This formula says that the maximum size of my ball would be given by surface tension gamma over density and gravity, right? A square root of that. If I plug the numbers for steel, for density and surface tension, I would get that the maximum size of a droplet in steel is just shy of 5 millimeters. Well, guess what? Welds are more or less that size, right? I think they're slightly bigger, but not much. And in any case, the bond, when we say bond equals 1, is like arbitrary. This is interesting because for this reason, you know you're not going to have welds that are 40 millimeters. You can't. It's going to splash all over, right? Super important. Also, look at this. Aluminum is lighter, has lower surface tension too, but all combined gives us that aluminum would have just shy of 6 millimeters. So aluminum welding and steel welding is more or less the same from the point of view of the bond number. And this is what gives you the size of your weld. And this is amazing, because if you remember, the size of the weld also gave us the heat input, right? Remember I said it's 0.6 kilojoules per centimeter per millimeter squared. And if I give you the heat input, I'm giving you also the cooling rate. We just saw that. So to some extent, the bond number, the effect of surface tension, is giving me cooling rate. That in steel is going to give me a hardness. So it's a miracle of God. It's incredible that when people welded steel, they knew nothing of this. They knew nothing. But all of a sudden, the surface tension force is making a weld that gives you the right hardness. It didn't have to be like that. It's a coincidence. But it's a happy coincidence. If things were different, people probably would not have welded steel. Right? So this is a very important formula. Now, there are super interesting questions. Let's say we weld in space, or we weld in Mars. When we all go to Mars to ride our Tesla cars. The gravity in Mars is about 1/3, right? So in theory, when we weld in Mars, everything is different. We can make huge welds now, if we want. That's amazing. So remember when we talked about gas-shielded flux core? One of the tricks of a gas-shielded flux core, you might say, if I have a gas, why do I want flux core? Well, with gas-shielded flux core, the flux is acting as a cradle of your molten metal. So you can have a bigger ball. You can start playing games with the bond number, because now you have a cradle that is keeping your molten metal in place. It's just amazing how everything in welding comes together. It's very few basic concepts. So I want to show you something interesting. I was talking with one of my friends in FabTech last year. It was after we taught the class. Or at the same time we were talking the class, but I think I had already taught this part. And he was telling me that when you're doing fillet welding in the vertical position, You go welding, but if you find a rusty spot in steel, the weld liquefies and falls apart. That's what he was saying. And I think this is awesome because it was speaking welder language. But it's not like that. I'll tell you my interpretation, but since I haven't welded, but this is my interpretation. When you're welding on clean plate, you have a steel that has relatively low value of oxygen because you're shielding it well. When you hit a rusty spot, you're going to have an amount of oxygen. So these curves here come from no oxygen and different amounts of oxygen. This is the activity of oxygen. And what this graph tells us is that for a rusty plate, our surface tension is going to come back to be lowered, right? In a rusty plate, surface tension is going to be lowered. Surface tension is what was holding our bead in place, in vertical up. We go to the very limit, right? We go to the very limit because on the flat position, the weld is kind of resting. But in vertical, the weld wants to fall. So what he saw is that when you hit a rusty spot, all of a sudden surface tension comes lower. And here he did the calculation. For no oxygen, low oxygen weld, you have more or less 5 millimeter bead that you can hold with gravity. But when you have a high oxygen, you'd have a 4 millimeter bead. If you were welding a 5 millimeter bead, when you reach the rusty spot, it's likely to just start running on you. It looks like magic to them. It looks like all of a sudden the material changed. But you would understand. Anyway, pretty cool. So morphology of the weld pool. I told you what would give this size. This is what a fast weld pool looks like. This is what a slow weld pool would look like. And that has implications for solidification. But there is a special class for that. I'm not going to worry much about it right now. This is very important. I put morphology of the weld pool, but that's the wrong title. What I want to talk about is about mechanisms of penetration. What gives penetration to the weld? Again, this is very important because there are defects called lack of penetration, right? Sometimes you want to have a full penetration weld. If you cannot have full penetration, you might need to have access from the other side. So penetration matters very much. There are 3 ways of generating penetration in a weld, in a fusion weld. One is the heat, whether it's a beam, whether it's an arc, whatever it is, in fusion weld, the heat reaches the surface, and then all this molten metal through recirculating flows and things like those is going to convey the heat and melt the liquid solid interface, right? As if you were like melting it just by the heat. When this is lasers, they call it conduction mode. But it's kind of a silly name because it's convection, not conduction. So I call it recirculating flows. This is typical of low current welds or low power beam, laser beam welds or laser cladding. Now, let's say we crank up the current. I did this in my PhD. Probably among the 10 welds I ever did in my life, right? So you crank up the current, and all of a sudden, what happens? Remember when we talked about the plasma and the pinch force? And the pinch force generated a jet, right? Now, this jet that increasing pressure with the square of the current, as I increase the current, it gets very powerful and pushes my weld pool away. Now, if the weld pool is pushed away, this heat is like eating away at the solid liquid interface. It's just essentially pushes the liquid away, and the arc is eating the weld pool itself. If you were to weld in this condition and you look at it, it looks almost like a dry bottom because this liquid here is so thin and the heat is just coming straight on the solid boundary. The mechanism of penetration here is very different than here. This is typical of submerged arc welding. And then the third penetration mechanism is like an extreme form of this. So this is the keyhole, in which you have strong evaporation, and the metal vaporizes and goes and create kind of a wormhole, right? A keyhole. And this can reach very, very deep penetration. When welders use 6010 and call it a keyhole, right? In reality, what they're talking is something like this, in which the very strong jet of the 6010, because it has hydrogen from the cellulose and constricts the arc, this very strong arc pushes the weld pool away. So they call this a keyhole, as opposed to the normal welding mode. But it's nothing to do with a keyhole from laser beam or electron beam. So I think this is a good point to stop. And we'll pick up next week. We have a break, and we pick up the week after. All right. Any questions about this before we move on? Yeah.
The LMAX that we saw earlier,
Yeah.
what exactly does that represent? If we have a single pass, for example, is it double thickness of the?
Right. Lmax, let's see, I put it here, is a characteristic length. For example, the height of the weld pool. Right. In this case, I was somewhat vague, because this number comes from relating these things as if you had a sphere. But it's not the same if you're welding in the flat position or in the vertical, right? So this L is some kind of characteristic size of your weld, right? And your weld, let's say, could be the weld width, or the total height of the weld, something along those lines. Right? But the weld, again, when we say 5 millimeters, you know we're not talking about 5 microns or 5 meters, right? That's what matters. Good? All right, let's stop here.